Hello everyone, I'm Lorenzo and today I will discuss Gothic ribbed vaults. I would have loved to ask you a live question. If you have ever stepped into a Gothic cathedral, have you ever wondered how medieval builders managed to create such imposing and luminous spaces? This question, along with other historical and cultural aspects, offers numerous insight into the contribution that medieval construction techniques have made to our communities. The construction of vaults is not merely a technical matter, it is also an expression of collective effort in context marked by limited resources and profound economic and social transformations. The Gothic heritage, which encompassed thousands of structures between cathedrals, churches, monasteries, civic buildings, and in some cases castles, represent a fundamental part of our cultural legacy. Understanding this legacy is indispensable for planning appropriate conservation interventions. Although estimates are not unequivocal, it is suggested that the number of Gothic buildings, particularly cathedrals and churches, may range between 5,000 and 10,000 across Europe, depending on the classification criteria used. The statistics on their conservation are fragmented and rely on national databases. To bridge this gap, projects and studies coordinated by organizations such as Europa Nostra are underway, though many records remain region-specific. In summary, the study of Gothic buildings is a timely and highly engaging subject that opens up important avenues for investigation, innovation, and research. After this brief introduction, I will outline the main points around which the presentation is organized. The first section frames the historical context and the motivation that spurred the evolution of construction techniques. The second section examines the various vault types: cross vaults, quadripartite vaults, tierceron vaults, stellar vaults, and fan vaults, highlighting their technical aspects. Finally, a comparison between the solutions adopted in Northern and Southern Europe will be presented. To speak knowledgeably about the technical and construction innovation that reached maturity during the Gothic period and that had a tremendous impact throughout Europe, it is necessary to briefly consider the preceding historical, political, and cultural context. By the year 1000, the threat of Saracen attacks along the Mediterranean coast had been subdued, enabling Masons to travel freely throughout Italy, the Alps, Provence, and even as far as Catalonia. This improved security facilitated travel along the Alpine passes, allowing monasteries and communities to thrive. Simultaneously, the economy underwent a profound transformation as labor began to be remunerated in coin. Thanks to this new economic system, local lords could support military forces and the church could hire itinerant builders, thereby promoting social mobility. The combination of a growing population, flourishing local economies, monastic reforms, and the absence of the Saracen threat allowed Masons to work wherever needed while receiving payment in negotiable currency. In this climate of renewed economy and cultural dynamism, the reputation of Lombard builders specialized in the use of brick spread beyond the Alps. Their influence led to the dissemination of construction techniques that, by integrating innovative aesthetic and structural elements, played a decisive role in the emergence of Romanesque architecture in Southern Europe. Meanwhile, Christian monks and clergy advanced into Central Europe and even further north along the Atlantic and Baltic coasts. Faced with the need to reformulate the Christian tradition according to a Frankish and Germanic model, architecture and related arts emerged as an expression of a new culture. The various vernacular traditions, the Mediterranean masonry tradition and the Northern timber tradition, intermingled, each adapting its distinctive characteristic to new requirements. The solid mass of the Southern construction tradition was transformed with renewed vigor by the precision of the structural innovation typical of the truss systems from Central and Northern Europe. The formal result was the Gothic cathedral, a culmination of great compositional sophistication that established the primacy of technical expertise, setting the dynamic course for our modern world. This triumph of human ingenuity can be described as unfolding in three critical phases, which can be simplified and schematized according to the theoretical framework proposed by Lynn Lancaster, building on the factors introduced by Schlebecker and White to better understand the roots of technical innovation as a stage in technological development. Specifically, the trigger for Gothic technical innovations was the drive to create larger, more luminous buildings. To meet this evident need, master builders transformed the curved surfaces of barrel vaults into sharply folded masonry surfaces. Thanks to the knowledge accumulated by the master builders of the Comasine tradition, later disseminated, developed, and preserved by the guilds, the emphasis on the curves at the intersection of different surfaces led to use of ribs. Aided by the evident optimization of resources, this technical innovation went rapidly accepted both socially and politically, evolving swiftly to replace heavy masonry masses with pinpoint supports and buttresses that directed the localized thrust of the ribs down to the foundations. A major technical breakthrough was achieved through the systematic use of cross vaults, which, unlike barrel vaults, do not require continuous massive walls capable of resisting the thrust transmitted by a curved shell-like surface. By reducing the masonry mass, which results in significant material savings, the available wall area of the windows is increased along the entire span, allowing the use of stained and colored glass to directly illuminate the naves. Romanesque builders had already intuited that vaults needed to be lightened to reduce the lateral thrusts on the walls. This process, based on intuitive principle of structural mechanics and, crucially, on the observation of similar structural collapses, a concept emphasized by Viollet-le-Duc, led to filling with mortar and stone an area extending just to the sides of the vaults. Consequently, the remaining portion of the vault became a relatively thin shell compared to the previous brick, stone, or concrete constructions. Multiple factors ensure that Gothic cross vaults possessed sufficient rigidity, making them particularly ingenious structural systems. Specifically, this refers to the combination of gravitational loads and lateral thrust, the binding function of mortar, the mechanical connection between elements in the folds of the vault panels, the geometry of the lightweight folded shell, and finally, the combination of these elements with both transverse and longitudinal arches. The fusion of the shell structure with a reticulated system, particularly well suited to supporting distributed loads, is the secret behind the great compositional freedom of Gothic structures. It is well known that constructing cross vaults by intersecting two barrel vaults poses significant challenges. The horizontal tangency at the crown of the vault tends to collapse as a single unit, adversely affecting the lateral thrust transmitted to the abutments. Moreover, the intersection of two semicircular barrel vaults produces an elliptical section, a geometrically weaker shape than a circle, thus making collapse more likely. Northern Italian Lombard mason between the 10th and 11th centuries resolved this problem by constructing dome vaults using diagonal semicircular brick arches, thereby freeing themselves from the constraints imposed by the intersection of two barrel vaults. Once this approach was modified, builders could vary the characteristics of the vaults to meet diverse requirements, bending and curving the panels to achieve a wide range of configurations. A further step Forward was taken at the end of the 11th and the beginning of the 12th century in Durham, England, Lessay, Normandy, and Aversa, Italy, where stone ribs were introduced in crossbows. The solution to the construction problem, which might also have been solved with advanced knowledge of projective geometry, a science still unknown to high medieval masters, lay in the example of the transverse arch. It became necessary, therefore, to adapt this solution by constructing the ribs of the diagonal arches before the vault panels, thereby creating a framework that functioned as a permanent stone centering. Essentially, this structure facilitated the execution of the vaults by playing a fundamental role in the construction process and providing additional bracing. By the end of the 12th century, master builders throughout Europe had acquired the geometrical skills required to design precise ribs for both square and oblong spans. Using lightweight wooden centering, the master constructed the arches and cut stone ribs, upon which they later built the vault panels, employing different materials according to local traditions. At the beginning of the 12th century, the clear advantage of crossbows with diagonal ribs captured the attention of builders throughout Europe. This new structural vocabulary for stone construction not only provided ease of construction, but also unified the vault with its support system into a coherent whole. The thrusts transmitted via the ribs were channeled through the shafts connected to the mass of the columns down to the foundations. The linear design of this complex structural system left a profound impression on builders, particularly those in Northern Europe, trained in the timber frame construction tradition. From the second half of the 12th century, architects and master builders began to stilt the arches along the lateral walls, the so-called formere arches, and the transverse arches to reach the height of the vault crown, thereby enhancing the efficiency of the clerestory. This solution was adopted in the construction of six-parted vaults when the large square spans of the main nave were flanked by two smaller spans in the side aisle. Invented in Normandy, it found application in northern France during the 12th and 13th centuries, even after the advent of pointed ribs had rendered them structurally obsolete. In the second half of the 12th century, master builders began to view cross vaults with ribs as a framed system where curved ribs were held in place by thin panels. The oblique and elevated vault series of six-parted vaults were soon abandoned in favor of a much simpler and faster technique, the pointed arch. Probably introduced after contact with the other Arab builders in the Holy Land and Spain, this intercultural exchange was the spark that definitely launched Gothic architecture. Carried to Northern Europe by returning crusaders, although already widely employed in Romanesque architecture in Burgundy and Lombardy, the pointed arch became in the 50 years following the 1150 the most recognizable motifs of Christian Gothic architecture. With this device, arches could be suspended between the lateral supports, and the transverse arches could reach the same height as the longitudinal arches without needing to be stilted. Particularly, in square spans, the profile of pointed arches were derived from centers located at varying distances along the impost line, as in the case of Tier's Point Arch, whose center falls at 1/3 of the span's axis. This transitional phase is well described by the Abbey of Saint-Denis and the Cathedral of Sens, Noyon, and Laon, all built in France between 1140 and 1180. New structural elements were introduced into the now obsolete Romanesque models, such as the attached column shut at Laon. Thus began a new period marked by freedom and flexibility in managing structural components, which allow the concentration of loads and thrust on isolated columns. The logic of the frame structure suggests the open, luminous, and airy space suitable for new requirements, which ultimately led to a complete rethinking of the wall structure to fully realize the potential of this new system. This approach proved so effective that by the early 13th century, masons were able to combine all three motifs into a new architectural synthesis. They constructed carefully curved and folded shells, supported by delicately ribbed frameworks, reinforced by slender buttresses and flying buttresses that stabilized the new, airy envelope. By the 11th century, medieval masters had understood that longitudinal barrel vaults, whether full or quadrant, using galleries or side aisle, were sufficient to support the thrust transmitted by massive barrel vaults, even though the solution blocked light from entering the building. A significant element of innovation came from the Norman workforces who, between 1019 and 1104, constructed the upper level of Durham Cathedral's coil. In this building, which retains the oldest crossbolts with stone ribs, the master chose not to use a continuous quadrant barrel vault to buttress the columns supporting the choir crossbolt. Instead, diaphragm walls were erected at each span, arranged perpendicular to the perimeter walls, with rounded openings that represent the archetype of Gothic flying buttresses. Although these walls were connected at a level below the optimal point for the flying buttresses, estimated at around 30 degrees, the imposing mass of the structure ensured stability. Demonstrating the competence acquired in just a few decades of intensive practice, when a few years later, in 1133, it became necessary to construct quadrant arches beneath the gallery overlooking the main nave, these arches were positioned at a higher level. This example represents a striking case of construction innovation, offering grading resistance to the returning moment transmitted by the main nave's crossbones. Although this solution still relies on intuitive and approximate responses to the challenges of precise bolt articulation and load distribution, its impact was so significant that it set the course for subsequent buttress construction in Gothic buildings. Indeed, in the general trend toward building ever taller, more luminous, and more spacious structures, it became necessary to devise a structural device capable of stabilizing the vault's thrust. While quadrant arches in a sub-roof still severely limited opening size, around 1175, the solution was proposed for the first time in the cathedrals of Saint-Denis and Vézelay, where these containment arches were shifted above the gallery roof and became exposed flying buttresses. The massive amount of material that had long been used to increase a wall's capacity to resist the overturning moment exerted by barrel vaults was gradually reduced to allow for recessed, independent window panels and reallocated externally to build isolated buttresses projecting at each span. This example aptly illustrates the analytical approach of Gothic architecture, in which builders were fully aware that excessively massive construction risked compromising the building stability. Instead, masses had to be precisely articulated, with stone carefully cut and dovetailed and placed only where necessary. A major breakthrough was achieved at Laon. Initially, builders reduced the triforium passage to a narrow walkway traversing the main nave's columns and significantly raised the clerestory windows. This resulted in buttresses that integrated well below the sides of the vaults. Subsequently, above each column, a quadrant arch was built over the triforium roof, inspired by the flying buttresses of Notre Dame in Paris. Positioned well above the previous buttresses, these exposed quadrant arches effectively stabilized the top of the main nave's columns against the thrust generated by the vaults. The lightweight, yet robust structural framework of arches and columns was thus permanently separated from the wall and the roof, becoming an enduring stone centering system. This structural configuration became the defining feature of the 13th century Gothic cathedrals, where the functioning of the load-bearing frame was emphasized, each truss carefully counterbalanced, with the wall becoming a screen rather than a support, and every element designed to fulfill a specific structural role. Consequently, the dimension of the rib voussoirs, so the thickness of the wall panels, which were reduced from around 30 centimeters to 15 centimeters, the profile of a column shaft, and so forth, were increasingly designed with precision. The Gothic cathedral thus became a technological artifact. With every part the result of a carefully conceived logical process, a comparative synthesis of the architect's knowledge and the craftsmanship of the builders. This approach laid the foundation for at least a century of structural rationalism that would profoundly influence architecture up to the 20th century structuralism. A further innovation was introduced in Amiens, when in 1220, Robert de Lusarche designed walls that reached over 42 meters in height, supported by slender columns. To contain the thrust of quadripartite walls, he employed for the first time a double series of slender flying buttresses, one positioned at the impost level and the second approximately midway up the wall's rise. In this manner, the thrusts were effectively counteracted and the walls stabilized against vibration induced by wind turbulence. The combination of buttresses, flying buttresses, ribs, columns, and vertical panels ensured that the loads were transmitted from the walls to the structural frame and ultimately to the ground without causing undesirable fissure in the masonry. To further emphasize the separation between the structure and glazed panels and to enhance the luminous quality of the space, when after 1194 the decision was made to rebuild the nave of Chartres Cathedral, the gallery was completely eliminated. This significantly increased the height of the clerestory windows, which were composed of slender single-light windows surmounted by circular windows. To achieve this dematerialization of the masonry, external buttresses composed of 3 orders of flying buttresses were constructed, with the first 2 connected by radial columns to increase rigidity. In this configuration, the visual emphasis shifted from the wall to the stained glass composed of small pieces of chemically tinted glass set in lead cames. The particular attention paid by medieval builders to structural stability is evident in Reims Cathedral, the coronation church of the French kings. Pierre-Jean d'Orbay, elected the architect of Reims in 1210, chose to build the cathedral according to the most traditional basilica plan, with the side aisle significantly lower than the central nave. The superimposed double flying buttresses were simplified into pure forms, and the pinnacles erected above the external buttresses were hollowed out and decorated with slender shafts to seemingly reduce their mass. Perhaps the most interesting device was the incorporation of membrane walls above the walls at each span, designed to absorb the thrust from the upper level of the flying buttresses and stabilize the columns. However, one must turn to England and wait until the 14th century to observe how designers began to employ a rib framework that did not concentrate loads and thrusts on isolated supports, but rather distributed them over a mesh grid of small linear elements. Essentially, a new approach to the static problem emerged that, by accepting a certain degree of indeterminacy, created an assemblage of interconnected elastic elements, none of which needed to be stressed more than the others. These Gothic bolts were designed as thin, rigid shells reinforced by a complex network of ribs, allowing architects the freedom to propose warped and twisted surfaces of double curvature. The thickness of the vault panels, which had previously ranged between 30 and 40 centimeters, were reduced to 10 centimeters, thereby greatly diminishing weight and, consequently, the thrust on the supports. As this load was then spread over a larger supporting surface, the Gothic vault evolved into a thin, reticulated shell with double curvature, enclosed within a relatively slender box-like system that ensured stability without the need for heavy external buttresses. To successfully complete this process, the ribs fanning out from the supports were increased, resulting in a smooth transition between the column and the vault shell. The formal codification of French Gothic in a grand yet limited formula tended to stifle further developments that could adequately respond to new challenges, since the pointed quadripartite cross vaults might not have required additional adjustments. However, as is well known, it was only the starting point for 3 subsequent centuries of technical experimentation and aesthetic elaboration. In this context, it was the English masons, through their independent originality, who opened up new possibilities for the evolution of medieval architecture. A first important step was the systematic introduction of the ridge rib along the apex of the vault. An emblematic example can be seen in the choir vaults of Lincoln Cathedral, designed by Geoffrey de Noyer in 1192, which marked the beginning of a new architectural phase. This solution emphasized the rib cage rather than the curvature of the vault panels. Furthermore, a second element was introduced, the tierceron, which connected from the vault's impost to the ridge rib at 1/3 of its length. English designers quickly explored the potential of this combination. In Lincoln, for example, Master Alexander conceived the first tierceron star vault above the main nave between 1225 and 1235. This formalized the configuration of a new vault type composed of transverse and longitudinal arches to which perpendicular ridge ribs and diagonal tiercerons were added, maintaining the basic form of the quadripartite vaults. The series of tierceron ribs effectively concealed the flatness of the vault panels, but the concentration of ribs overly emphasized the supports rather than the vault crown. Therefore, in the 14th century, English masons and architects addressed this aesthetic issue by introducing a new structural element: a short, straight rib that connected the tierceron in a meshed pattern, further distributing the loads. These are known as lierne, and they help create a structural grid in the upper part of the vault. A first notable example is the elaborate lierne vault constructed by John Weisbeck in the Lady Chapel of Ely in 1321-1339. Here, the curvature of the shell was hidden by a radial arrangement of tierceron interwoven with the vault crown, and subsidiary lierne were added to create both a decorative and structural grid. In short, the solution produced a lightweight, economical, and fire-resistant structure that was relatively simple to construct and significantly reduced the timber required for centering. Moreover, it segmented the smooth vault surface into manageable portions, contributing to the development of an optimally lightweight configuration. By the end of the 14th century, English masons had defined a mature variant of continental Gothic, imposing a distinctive framework logic on their structures. Builders in the northwestern Europe moved beyond merely assembling structural components to create new patterns of vault panels and ribs. Instead, they charted a new course for radically reconfiguring the transition system between the main nave and the side aisle, a system that had long posed compositional challenges for medieval churches. The overriding theme remained interior illumination and spaciousness. Thus, beginning in the early 14th century in England, several solutions were developed to free buildings from clerestories and flying buttresses that had previously challenged medieval construction ingenuity. The structural and formal evolution of various 14th century attempts quickly led to a new, bold solution, the flying ribs. These are essentially ribs that radiate in a fan-like manner from the pillar and extend to the ridge line, the keystone, or other secondary ribs, thereby bracing the structure by providing an intermediate support point. However, it is in the 15th century that the vaulted structure experimentation reached its peak, particularly with fan vaults. Rejecting the elaborate traditional apparatus of intertwined ribs and geometric patterns, English architects began constructing vaults where these elements became secondary to the shell surface. The study of the stereotomy of vaults constructed by John Wastel at Peterborough between 1496 and 1508 shows how advanced late Gothic masons had become in developing shell structures. The vault in the retrochoir of the cathedral is built with meticulously modeled panels and voussoirs, with only the lower register constructed using a rib and panel method. The remainder of the decorative ceiling pattern acts as a device by which excess material is removed to lighten the large flat stones of the shell. In this example, Gothic architecture reaches its culmination. The original principle of a framed skeleton filled with panels is replaced by a complete, autonomous structural shell, a static device of great refinement in which the voussoirs balance within a complex system of thrusts and counter-thrusts within a three-dimensional continuum of stone and masonry. As is well known, there are significant regional differences in the interpretation of Gothic models. In this presentation, the focus is on those developed in Central and Northern Europe, particularly in France and England, where the opus franciginum had truly flourished and reached unparalleled peaks of technical and construction virtuosity. In Northern Europe, inverted T sections are preferred, with the central nave significantly taller than the side aisle. This solution necessitates the construction of external buttresses and flying buttresses to allow greater interior illumination. In Southern Europe, however, the long-standing tradition of hall churches and a reduced need for interior illumination led to the construction of buildings with nearly uniform sections between the side aisle and the central nave. This design choice appears almost as an obvious response to avoid the need for complex flank arches, and it was adopted in the hall churches in southern France, Spain, and many Central European structures, ensuring that Gothic experimentation proliferated until the 16th century. Across the Pyrenees and along the Mediterranean coast, medieval architects continued to construct buildings with massive walls long after the Normans and Parisians had shifted toward framed structures. The emphasis on load-bearing walls greatly simplified structural issues by dissipating loads and thrusts through the heavy masonry mass of the walls and buttresses. In response to the Northern European tendency to build hall churches in Saint-Pierre Cathedral in Poitiers in 1162, the naves were constructed at approximately the same height, creating the effect of a single vaulted hall. Albi Cathedral in 1282 was built as a single hall structure, influencing the design of Girona Cathedral in Catalonia, where about 2 centuries later, Guillermo Bofill would construct a single nave of 22 meters wide, the widest vault ever realized in a Gothic cathedral. The construction of these structures followed a complex and orderly process. For sizable buildings, the construction of a vault began with a wooden platform built above the impost of the lateral and transfer arches, itself supported by braced props and anchored to the columns and piers. On the platform, The lines of the reefs were drawn as references for precisely constructing the semicircular arches in space. In some cases, the geometry of the diagonal arches was also traced on these platforms, though more often it was inscribed on the roofs or the floor. In Northern Europe, or in regions where climatic conditions necessitated a pitched roof to protect the exodus of the vaults from rain, snow, and ice, the roof's reticulated beams were used to move the loads with lifting machines, drums, and winches. In Central and Southern Europe, where Gothic cathedrals were commonly built with flat roof terraces, construction proceeded from the bottom up, using movable wooden centering, first determining the exact position of the keystone. Only afterward was the permanent stone centering, composed of the reeds, constructed. At that point, the vault series were built. They could be constructed up to 2/3 of the vault's rise without centering, and the final portion with lightweight centering composed of generally paired boards. In summary, the study of Gothic vaults reveals a continuous path of evolution, historical evolution, from a construction tradition that, following the consolidation of favorable political and economic context, led to the creation of larger and more luminous spaces, to the emergence of the Gothic cathedral, a result of the interplay between masonry tradition and structural innovation. Evolution in the construction techniques, the introduction of ribs from cross bolts through tierceron to flying ribs and fan bolts, demonstrate a continuous refinement of load distribution systems and thrust management, which revolutionized stone construction, and poses important conservation challenges. The fragmented nature of available data and the complexity of these structural systems underscore the need for targeted conservation intervention and an in-depth understanding of both the original techniques and the conditions of decay to preserve this heritage authentically for future generations. This journey of innovation not only marked a turning point in the way buildings were conceived and realized, but also laid the groundwork for the structural rationalism that would influence architecture up to the 20th century. Thank you very much for your attention, and I wish you a nice evening.